Hi guys, here is MIH. It's been nearly 2 months since my last video, and that is because I'm doing a series of smaller projects that I thought are not that worthy of being posted. But anyways, today I'm demonstrating how to build your own chlorate cell from common materials such as a reagent bottle and plastic pipettes. As you can see, the lid of the bottle is where nearly all of the work is focused on. It consists of 3 parts: 2 titanium wire cathodes sticking out of tubes made from pipettes, and a large piece of MMO mesh anode. The electrodes penetrate the lid and can be connected to the power lines. The 2 small caps, which are also made from pipettes, on the top of the tubes serve to keep back the salt mist and preventing corrosion of electrical connections. Note that the titanium wire was bent on the top and sticking out on the side instead of being straight. This allows the 2 wires to be connected to the same power lead and therefore maintain a rather even current density to protect the anode from corroding and to maximize the efficiency. The bent wires also prevent salt mist from reaching the electrical connections and destroying it. Okay, now we will have a closer look of how the parts are connected to the lid. The center MMO anode is hot glued to the cap on both sides. However, I didn't use any glue to fix the tubes, as I found the salt creep to be minimal and doesn't impact the cell, and also because I have a specialized method of sizing the hole to make a nearly perfect fit. First, heat a thick iron wire and poke it through the lid to create a small hole. Then, heat the tweezer with the blowtorch and spin it in the hole to enlarge it. You can repeat this step until the hole diameter is just slightly larger than the diameter of the pipette, and then insert the pipette through the hole with the aid of maybe a glass rod. By the way, the tube should not reach the surface of your electrolyte, or else the gases formed may cause a lot of foaming. Now let's take a look on the seal of the anode. You can't see a lot of glue on the 2 sides now, but when I made it, I put a lot of glue on to ensure that absolutely no salt could leak over. Putting a lot of glue is also a good thing to do when you run your cell at a high current, because when the temperature of the cell is too high, the glue partially melts and flows down as the yellow stain on the electrode. This will slowly deplete the glue on the seal, as well as possibly contaminating your electrolyte. So try to find a current that heats the cell to around 60 degrees Celsius to avoid melting the glue. I usually use a constant current of 3 amps. So as you can see, this cell is basically built for very high reliability. Nearly every design is made for reducing or eliminating corrosion. And in fact, I continuously use this cell for 5 weeks with minimal maintenance, and it worked perfectly. Finally, we inspect another major part of a chlorate cell, the power supply. I'm using an AC to DC 12V 5A adapter made for charging car batteries or something. Both the voltage and the current needs to be high enough, as higher current shortens the electrolysis time, and to complement the current, a decent voltage is required. I usually run my electrolysis under a constant current, which I can easily achieve by using the constant current mode on the small module. As you can see, the digital display shows the input voltage, output voltage, current, and power successively, rendering it very useful. When I short out the power leads, the output voltage quickly drops, while the red and blue LEDs light up. By switching the display to the output current, I can see the maximum current in the constant current mode, which I've set to be 3 amps. For my cell running under 3 amps and in its operating temperature of 60 to 70 degrees Celsius, I need roughly 5 volts, but as the cell runs and the chloride ions are depleted, the voltage will rise. I recommend stopping when the voltage reaches 7 volts at the operating temperature. Note that the resistance of the cell decreases as temperature increases, so only readings at the operating temperature are accurate. So there you have it, how to build your own chlorate cell and set up a ready-to-go power supply. The next videos will be making potassium perchlorate again from potassium chlorate, and then making rocket fuels using it. See you soon!